All right, so we are transitioning from functions into linear functions, and we're going to be covering all types of equations for linear functions. And one thing that's essential for a linear function is slope, because it describes kind of the aim of our line, the angle, the steepness. So we're going to get into all of that. Hopefully some of this slope stuff is a review and it comes back quicker than you guys think. So just a little review of some vocabulary. We have our x value, which is our independent variable. It's a variable in a function that we get to choose. So, we plug in various x values that we came up with. Usually we did -1, 0, 1, 2, something like that. Dependent variable is the y value, or it could also be considered, my pen is not working, could also be considered f of x. So I'm just going to add that here. And this is the variable that depends on the value of the independent variable. So whatever we plug in, the input will determine what our dependent variable, our output, or our y value becomes based on the function rule. So for a linear function, it has to be a function that the graph forms a line. One of the first type of forms for the equation that we'll be going over is this one. It should maybe sound a little bit familiar, y equals mx plus b, and then I've just added f of x in there because y and f of x are interchangeable. So a linear function has one independent variable and one dependent variable. So here's our independent x, and then our dependent is our f of x or y. And then here are just some examples, again, of linear functions. We did cover this once before, but we have a linear function. If it's curved, it's not linear. This right here is actually not a function. We'll still be looking at lines that are vertical like this, but we just have to remember that they are not a function, and it will actually go into like the fact that they don't have a slope too. We have a linear function right here, horizontal, and then we've looked at this graph before. This is actually a square root function, or a square root relation, and it's not a function. It doesn't pass that vertical line test. We could, draw a line through here and see that it touches twice. Okay, so we can identify linear equations or linear functions from their equation, like I just showed on the previous slide right here, our y equals mx plus b form. Or we might be looking at a table and being asked if our function or our relation is linear. So I want you to think back to arithmetic sequences that we were just working on. Now, most of our arithmetic sequences started with a 1, so that might be a difference right here. Our x values can go into the negatives. We'll use 0. But what we see on the output is that if we're going consecutively through our input values, just, going up by 1 integers, then our output values for y will also have this like common difference, which is exactly why we went over arithmetic sequences first. You see this common difference right here each time we're subtracting 3, and this is how we're going to identify if a function is linear from a table. So we should see this common difference right here if our input values are increasing or decreasing consecutively. Now, if our input values are jumping around, then we are going to maybe not see consistency over in the y's, and we may have to readjust. Okay, so we have slope, and a phrase you may remember for slope is rise over run. We're going to be transitioning to some new notations for slope. So when we are referring to rise, we're talking about the vertical change. And vertical change goes with our y values. And this symbol that I have right here is called delta. It actually means change in. So when we see that triangle in math, that's referring to change in, and we'll use it throughout math that way in future classes. So change in, and that's delta. So we have change in y, our vertical change, and then we have our horizontal change, which we refer to as run, and this right here would read change in x. So if we look at an XY table, and I already have it laid out here, we want to look at our change in x, our change in y, similar to what I was just showing on the last slide, but now we're actually looking at our input values too. So as our input values are consistent, we are increasing by 1. If we graphed all of these, we would see that in between each of these points, that increase of 1 is running to the right 1 space. And then our y values are all increasing by 2. And we would see that vertically, that's going to be going up 2 spaces on a graph. So the slope would be 2 over 1, which simplifies to 2. Now over here, we see our x values not going up by 1 this time, going up by 2, but that is just okay. We just want to see consistency on both sides. So we can see we have a consistent change in x here, and that's going up by 2. We have a consistent decrease in y here, going down by 2, and we're putting change in y over change in x, so negative 2 over 2, which simplifies to negative 1. Okay, so we are just going to look at some different designations for slope. So we have 4 different types of slopes for directions, and positive slope is going up from left to right. Negative slope is going down from left to right. A 0 slope is going to be flat. This is no change. So when we were looking at our functions, we said, their distance was constant. They were staying in the same spot. That was a 0 slope. Then an undefined slope is a vertical line. It's undefined. We had said that this isn't even a function. We'll talk more about why it's undefined, but that's how we refer to the slope. And this is also, in our functions stories, when we were looking at those, this is the one where it's like, this graph doesn't even make sense. They're time traveling, and that's because, functions of time and distance actually are functions, and this isn't a function right here. Then we have just steepness. So not steep slope is going to be a fraction. The smaller the fraction, the less steep. And then our steepest is going to be whole numbers. And then you can kind of just order them by going from our smallest number up to our largest number for steepness. Now, if we go into the negatives, that reverses. We're kind of looking at absolute value, like what the actual number is. So if I had a negative 4 as a slope here, that is going to be steeper than a slope of negative 2, steeper than a slope of negative 1, steeper than a slope of negative 0.01. These would just be going down instead of up. Okay, so now we're going to be getting into our slope formula. So here we have it again. Slope is change in y over change in x. And if we're referring to 2 points that we're finding the change in between, our first point could be called x sub 1, y sub 1. Sometimes we'll just say x1, y1. And then our second point is going to be x sub 2, y sub 2. This doesn't have anything to do with exponents. It's just a way to refer to 2 different points here. Our first point of x and y values, second point of x and y values. we couldn't just use x, y because, you know, they're going to be two different values and we can't assign just one variable. So if we want to calculate the rise and the run, we're going to be using our slope formula. Now, you know, thinking back to what we were doing in this table, I'm going to just go back a couple slides. You know, how are we getting from -5 to -3? We're actually taking -3 minus -5. You know, when I do that, I end up adding my double negative. -3 plus 5 is 2. So the way I actually get that common difference or that change in y is by subtracting. You know, I didn't really do that here. I just looked at it and could see, but, you know, that's the operation that would get us that number of 2. So going back to the formula, that is the reason why we are subtracting. We take our second y value, we subtract our first y value, and then we do the same with our x's. So and this is going to be our change in y, and it literally tells us how much did y change and how much did x change. So here's an example. If we have 2 points, we're going to want to first start out by labeling them. So I write them down and I label x1, y1, x2 sub 2, y sub 2. Then I start plugging it into my formula. So I had labeled y sub 2 as 1. I write that first. I go to my other point, subtract y sub 2, subtract y sub 1. So I subtract 5. In the bottom, I'm going to take my x sub 2. Now, if I start with 1, I have to start with 8. That's very important that the first two numbers in our subtraction are coming from the same point. I take 8, which is x sub 2, and subtract 2, which is x sub 1. Then I just work it out. 1 minus 5 is -4, so you know we're getting our integer operations in here. That's going to be important to get the right answer. And then 8 minus 2 is 6, and then we're going to need to simplify our fraction, divide by 2, and get -2 over 3. Now, you know, if we actually look at counting the slope, we went down 2 over 3, and that got us to the line. Our original slope before subtracting was down 4, so 1, 2, 3, 4 over 6, 1, 2, 3, 4, 5, 6, and then that just simplifies to get me this -2 over 3. Now, if you notice, this should look something like what we have been getting as one of our evaluate questions, and that's where it shows a line, it's showing two triangles, and it's asking about them being congruent. Now, these are not congruent triangles, they're similar triangles, and that's because, you know, the size and shape of this one is, the shape is the same, size is different, and that's just how it's going to work out with slopes. If we take any triangle, you know, even this one, even though that was like a decimal that I'm not even sure about, when I take the slope, it's going to be an equivalent fraction of these where it can simplify and is therefore similar. Alright, so this is going to be our last example. I don't want my video to go over 15 minutes, so I have 1 minute and 15 seconds left. So we have 2 points and we want to find the slope of the line that passes through them. First thing I'm going to do is label my 2 points. I have x1, y1, x2, y2. Now, I would like you to pause the video and see if you could work this one out on your own based on what I just did on the last example. All right, so we're back, and this is how I worked it out. So I labeled my point. I took my y2, which was 0, subtracted 3, which was my y1, took my x2, which was 2, subtracted x1, which is 1, and then worked it out. I got a -3 over 1, which is -3. Another way I could think about doing this is taking the points, you know, putting them in that table-like format, stacking them on top of each other, and I could see that to get from 3 to 0, I would be subtracting 3. To get from 1 to 2, I would be adding 1. And that is it for your notes today.